Today's numerical is maximum bending moment of simply supported beam is 10 kN meter. The cross section of the beam is as shown in the figure. Find the maximum bending stress in tension and compression. See this cross section, rectangular cross section with this hollow square inside it. So first find neutral axis for this cross section. To find neutral axis, use formula y bar is equal to a1 y1 minus a2 y2. a2 is this square area. This is hollow square inside this rectangle. That's why minus sign we use. Deduct this square part. a2 and y2 is centroid distance for the square from bottom fiber, and a1 is area of this whole rectangle, and y1 is centroid of this rectangle from bottom fiber upon a1 minus a2. Now a1 is area of whole rectangle 120 multiplied by this 20 plus 20 plus 20 is 60. 120 multiplied by 60, 7200 square. Y1 is centroid for this full rectangle is 120 upon 2. It means 60 mm. A2 is area of this hollow rectangle. See, this side is 20 mm and this side is 20 mm. 20 multiplied by 20, 400 mm square is A2. And Y2 is equal to centroid for this hollow square is 20 by 2, 10 mm, and from this bottom fiber to this distance is 20 mm. So 20 plus 10, that means 30 mm. 20 divided by 2, this distance, and plus 20 mm is this distance. (30 mm). Therefore, y bar is equal to a1 y1. a1 is 7200 multiplied by y1 is 60 minus a2 y2. a2 is 400 multiplied by y2 is 30 divided by a1 minus a2. 7200 minus a2 400. 61.76 mm is centroid for this rectangle with hollow square part inside it. So here something here, this is neutral axis, or you may call it centroid for this rectangle y bar. Now next find moment of inertia I is equal to I xx1 plus I xx2. I moment of inertia is equal to moment of inertia for this whole rectangle. First calculate whole rectangle moment of inertia and minus deduct this square rectangle moment of inertia. So here a1 I1 ixx1 minus sign, and this ixx2 is this hollow square moment of inertia. Ixx1 is Ixx1, that means here center of this full rectangle is something here 60 mm, that means below this neutral axis, something here x1 x1. So ix1 ixx1 is this 60 as it is multiply by 120 cube by 12 plus area of this whole rectangle 7200 and multiply by distance between this neutral axis to this distance between neutral axis to this rectangle neutral axis distance. So 60 into 120 cube by 12 plus sign here area of this full rectangle is 7200 multiply by square of this distance between neutral axis to this whole rectangle neutral axis distance is y bar minus, that means 61.76 minus 60 mm. This y bar is 61.76 and this distance is 60 mm. This 60 mm. This y bar minus 60 is this distance. So 61.76 minus 60 mm. And square of this plus this hollow square moment of inertia. For hollow square moment of inertia, here x2 and distance between this x2 is this said 20 as it is 20 into 20 cube by 12. That means moment of inertia for square is a raised to 4 by 12. That means 20 raised to 4 by 12, or write in this form 20 into 20 cube by 12. That means 20 raised to 4 by 12 plus area of the square is 400 mm square. 400 multiply by distance between this full section neutral axis this to this x2 axis distance between this neutral axis to x2 axis distance is this distance is y bar, that means 61.76 mm, and minus this distance, that means this distance y bar minus this 20 plus 20 by 2 30 mm. Y bar minus 30 mm is this distance. Y bar is 61.76 minus 30 mm. Therefore I is equal to this 61.76 minus 30 and minus 60. 61.76 minus 60 square of this term multiply by 7200 plus 60 into 120 cube divided by 12 is 8.66 into 10 raised to 6. This term is 8.66 into 10 raised to 6 plus this term is 61.76 minus 30 square of this term multiply by 400 plus 20 into 20 cube divided by 12 is 0.4168 into 10 raised to 6. Moment of inertia is equal to 8.66 plus 0.4168. 9 mm raised to 4. 9 into 10 raised to 6 mm raised to 4. So, by using bending equation, use formula of bending equation m by I is equal to sigma by y, or flexurer formula, using flexurer formula or bending formula, m by I is equal to sigma by y is equal to E by R. M by I is equal to sigma by y. Sigma T, tension side. Stress at tension side is equal to m by I into y t, distance from neutral axis to topmost tensile fiber distance. M is 10 kilonewton meter. That means 10 into 10 raised to 6 Newton mm. And yt is distance from neutral axis to tension side end compression end tensile fiber. This is 61.76. This much distance from neutral axis to extreme tensile fiber. That means y bar 61.76. Divided by I. I is moment of inertia, and we calculate moment of inertia. It is 9 into 10 raised to 6. 10 raised to 6, 10 raised to 6 get cancelled. Tensile stress is 10 into 61.76 divided by 9. 68.62, and unit of stress is Newton per mm square. So see, this 61.76 is in mm raised to 4. This moment of inertia is in Newton mm. this moment of inertia is also mm raised to 4, and this yt is only mm raised to mm into mm, topmost mm into mm is mm square. That means, and mm square and this square cancel, that means Newton per mm square. Yes. Sigma T is 68.62 Newton per mm square. That means tensile stress is 68.62 Newton per mm square or MPa. Newton per mm square and MPa are similar. By using same this flexural formula or bending equation, m by I is equal to sigma by y, calculate compressive side stress. That means sigma compression is equal to m by I equal to sigma by y. This is yc. M is 10 into 10 raised to 6 Newton mm, and yc is 120 minus 61.76. That means 58.24. This distance. This distance is this 120 distance minus this y bar distance. 120 minus 61.76 is 58.24. And divided by I, moment of inertia. Moment of inertia is 9 into 10 raised to 6. 10 raised to 10 raised to 6 get cancelled, and sigma c is equal to 10 into 58.24 divided by 9. That means 64.71 mm is stress at compression side. Yes, 64.71 mm. Sorry, Newton per mm square, not mm. Newton per mm square or MPa. So, see here. This is neutral axis. Compression side is 64.71 and 68.62. That means the bottom tensile side stress is greater. And at neutral axis stress is 0, and at compression side stress is 64 point sigma c, sigma t. Sigma c is 64.71 MPa and sigma t is 68.62 MPa. So these are stresses. Compressive stress is minimum as compared to tensile stress for this section. Tensile stress is 68.62 MPa and compressive stress is 64.71 MPa. For this simply supported beam of this cross section, bending moment for maximum bending moment is 10 kilonewton meter, and cross section is 120 mm by 60 mm and one square hollow part inside it. Compressive stress is 64.71 MPa and tensile stress is 61.62 MPa. Thank you very much.